This is section 4.4, modeling nearly exponential data. In section 4.3, we actually looked at modeling data that were exactly exponential, and there was actually a nice little formula to do it. We didn't have to take out a calculator to do a regression. Now, even if the data are exactly exponential, you can still use the technique that we're doing now in order to get the model. So, exponential regression. Okay, we've already seen how to model data that are exactly exponential. Okay, we did that in section 4.3. Okay, remember we looked for y equals a times b to the x power. Now again, what we're doing now can also be used for the data that we saw in 4.3. Remember, in order to be exponential or almost exponential, to go from one y value to the next y value, you always multiply by the same non-zero constant, which means that the ratio of consecutive y values are either exactly equal to one another or almost equal to one another. Now, in trying to decide if we should use an exponential model, we can look at the context of the problem, or we can graph the data to see if it looks exponential. Typically, whenever we're talking about growth and decay, we're looking at exponential models. Now, in the next slide, we're going to look at the exponential growth and exponential decay again. So, for exponential growth, we expect the data to line up like the following curve. Okay, more or less like that, which means, kind of in the beginning, it's not growing very fast, but then after a certain point, it grows really fast. Notice this is increasing concave up, which that means that the rate at which it is increasing is also increasing. For exponential decay, we expect the data to line up like the following curve. Okay, it's decaying or decreasing very rapidly at first, and then it starts to slow down. Notice again, it is concave up, but it is decreasing concave up, which means the rate at which it is decreasing is actually decreasing as well. Okay, some examples. Okay, number one, the population of bass in Lake T years after the year 2010 is given in the following table. I want to answer the following. Find an exponential model, P of t, that gives the population of bass in the lake T years after the year 2010. Round the values to 3 places to the right of the decimal point. And in question B, plot the data and the graph of the exponential model on the same set of axes. Use an appropriate viewing window. Now, in terms of actually using an appropriate viewing window, notice the x or the t values go from 0 to 5. And for the population, we can go as low as 0 because you can't have negative population. And it looks like I need to go past 2,680. So we'll kind of keep that in mind when we start plotting the points and drawing the graph in the calculator. So our solutions. Okay, in part A, to find the exponential model or exponential regression, we follow these steps. So basically, these are the steps to get an exponential regression. So, step 1, enter the data into the list. We put the t-values, the independent variables, into L1, and the functional values, which are the dependent values, into L2. So remember to do that, you're going to press stat, and then enter and enter. And we're going to start putting the entries in. So let's see, let me go back to my list here. So we take out our calculator. Okay, so it's going to be stat. We're editing. Okay, now remember L1s were what? 0, 1, 2, 3, 4, 5. Yeah. So 0, press enter. 1, press enter. 2, press enter. 3, press enter. 4, press enter. 5, press enter. Use your navigation keys to get to L2. Okay, so we're having 200. Enter. 340. Enter. 565. Enter. 955. Enter. 1590. Enter. 2680. Enter. And then we can quit that screen. So let's get caught up to where we are. Okay, so we've entered our list. Actually, our data is into lists, I guess I should say. Step 2, we quit the above screen, which we already did. Now recall from our experience with linear models that we need to press the Stat key again. Okay, so we're going to get the following screen. And remember, since we're trying to find a regression model, that means we're doing a calculation, C-A-L-C. So step 3, we're going to perform a calculation with our data. We scroll to the right to highlight calc, and you get this screen. Okay, now remember, you scroll through all these to figure out which regression you want. We already did choice 4, and notice the one that's for exponential, it's not quite there, so we're going to have to scroll down a little bit. So let me get caught up again here. So stat, it's calc. Okay, now I'm scrolling down looking for what looks like exponential regression. There it is, E-X-P-R-E-G. If you remember that's choice 0, that's the number 0, not the letter O. You can just press 0 on your keypad and it'll come up. So we press enter. Okay. Now again, the X list is in L1, the Y list is in L2. The frequency list we don't care about. Now remember, since I'm going to be doing some graphing and calculating with it, let's store this regression equation that we find into Y1. So we're going to do vars, Y vars, press enter, and press enter. Okay, so now it's in Y1. So to get caught up here, so when I do the regression, we go down to EXP, remember that's actually choice 0, so you can press 0 on your keypad if you want to go straight to it. Okay, and then when it's highlighted, you're going to press enter, and you get this screen. Now remember, that's the t or x values. These are the functional values. And then we're going to store the regression equation in location Y1 so we can graph it. So remember, X list is where the independent variable values are stored. Y list is where the dependent variable values are stored. Now, if for some reason you store your X's and Y's in different locations, you are going to have to change those. That's why it's best to use L1 and L2. That way you don't have to worry about how do I change it. So depending on how you may or may not be able to do the next paragraph. You know, putting the regression equation into location Y1. So we've done all that. Okay. So we're caught up to there. And we're getting ready to calculate. So to calculate the regression equation, you're just going to scroll down to calculate and press enter. So let's see if we can do that. Okay. Scroll on down to calculate. It's flashing over it. Press enter. Okay, and there are our coefficients. We're going to have 201.052 times 1.679 raised to the x, or I guess I should say to the t power to correspond to our variables in the problem. So there we are. Remember, we were supposed to go to 3 places, and I didn't set my mode float to 3, so I'm going to have to round it manually. So P of t is 201.052 times 1.679 raised to the t power. So there's the answer to part A. Okay, for part B, where to plot the points in the graph, we need to change the window settings. Okay, remember our largest x value was 5, and the largest value was 2,680. So for the x, or the t, I guess it makes sense to go 0 to 5. So these are my window setting. Okay, I went a nice multiple of 100 past 2680. So if I set up my window here, so quit this, window, come on, window, 0 for the minimum x, 5 for the maximum x, keep the scale at 1, the y min of 0, maximum of 2700, and my scale was 200. And then we can quit that. Okay, now remember, we're doing a statistical plot, so to get caught up here, I'm going to need to turn on a stat plot. So I'm going to choose to turn on plot 1. So here are the steps to turn on a stat plot. So you're going to press stat plot, which is the second of y equal. Okay, so 1 is already highlighted. So I just press enter, you get it turned on. Okay, now you're going to scroll down and highlight on and press enter, and this is the graph, that one right there, that does the scatter plot. Remember, that's basically what we're doing. And again, the x list and y list are what they're supposed to be. I'm always happy with what they have as their dot for the graph, and I always keep my color the same as they have. No sense of confusing myself. So, to get caught up here. So, second, y equal to get stat plot. Press enter. On is flashing. Turn it on. Okay, everything I want is fine. So now all I have to do is graph. It will plot the points, and it will also draw my regression model. You can see it actually does go through them fairly well, and may not go through them exactly. Like, you know, this one looks like it's a little bit below. It doesn't hit the dot exactly, it's a little bit above. So there all that stuff is. So there's your graph for the model itself and the points. Now remember, I've given you instructions on how to download the TI-84 calculator into your computer. Okay, it's in the content browser area under calculator, and when you open that folder, it's virtual TI-84 that you want to look at. Okay, now again, notice that the graph does a good job of approximating the data. Okay, sample number 2. The table below shows the quantity of radioactive substance that remains from a 100 kilogram sample T hours since we first obtained it. So I'm starting with 100 kilograms. So answer the following. Now, it'll be interesting to see whether or not our model actually gives A to be 100. So part A says, find an exponential model, Q of T, that gives a number of kilograms remaining T hours since the sample was first obtained. Round your values to 3 place or out of the decimal point. Question B, using the model from part A, how many kilograms remain 24 hours after the sample was obtained? Write your final answer to the nearest hundredth of a kilogram. Part C, find the half-life of the substance. Round your final answer to the nearest tenth of an hour. And question D, plot the data and the model on the same graph using an appropriate viewing window. Okay, now notice our T goes from 0 to 15 in multiples of 3. So we can figure out the x min and x max from an appropriate window. And if we look at our quantity, which is our y, it ranges from 100, but of course we're going to go down to 0. And it keeps going down to 52.9. So notice that is the largest. So my y min is going to be 0. And for my y max, I'm going to go slightly above 100. That way I'm not completely at the top. And if you like, you can say 100, but you know, it's kind of up to you. Just don't go any smaller than 100 for your y max. Okay, while you're copying that down, let me get my calculator set up. So quit all this. My y equals. Clear that out. And second, quit that. Okay. Okay, our solutions. For part A, we enter the t values into L1 and the q values into L2. So again, I got to go back, see the data. So, calculator, stat, enter. Okay. Oh, if you want to clear out the list, let me try to do that. So let's quit this. Okay, to clear out those lists, that way you're not confusing yourself, because if you enter new values, it will type over them. But you just do second plus, which is memory, and you want choice number 4, clear all lists. So press 4 and then press enter. So the lists are all empty now. So let me clear that too. Remember, it was second plus and choice 4, press enter. Okay, now I want to get rid of that. Now, stat, enter. Okay, I got to scroll back to L1. Okay, so let's see. 0, enter. 3, enter. 6, enter. 9, enter. 12, enter. 15. Okay, got my t values. Okay, then 100, enter. 88.1, enter. 77.8, enter. 68.5, enter. 60, enter. 52.9, enter. And we quit that. So we've got our data entered into list 1 and list 2. Okay, we're going to quit that screen. We're going to do the exponential regression. We're going to go into Stat, Calc, Exponential regression. Remember, exponential regression is choice 0. So again, since we're going to graph the model and maybe do a calculation with it, we're going to store the model into y1. And to save myself some agony of trying to figure out how to round too much, no, I'll leave it alone. So do Stat, Calc, remember, choice 0. Okay, we want to store this into y1. So vars, y-vars, function y1. Okay. Now, if I had not cleared out my y1, this would overwrite it. So calculate, and there we go. Notice we know it was actually 100 for the A, the initial population, but it's not exactly so. You know, it's close though. Okay. And then when we round, we get Q of t is 100.155 times 0.958 raised to the t power. Okay, now Q of t, part B wants us to find Q of 24. Okay, right? So wanted to know how many kilograms after 24 hours, and we're going to the nearest hundredth. So since we have it in the calculator, we can do, okay, let's quit this screen. Vars, vars, y-vars, enter, y1 of 24. Close parenthesis. And to the nearest hundredth, 36.11. So we have to the nearest hundredth, 36.11 kilograms remain after 1 day, after 24 hours. Then question C wanted us to find the half-life. So we're going to use the crossing graphs method. So we want half of what we started with. Remember, we started with 100, so half of that is 50. So in our calculator, okay, clear this one out. Y equal. Okay, so Y2 is going to be 50. Okay. And now it may be time to start thinking about the appropriate viewing window. So my window, again, I use 0, 21, 3 by 0, 1, 20, 12. Okay. The reason I went out to the 21, even though the value I went out to 5, is I got to be sure I go far enough out to see the graphs intersect. Because if you didn't, you'd have to go back and change your X max. So window 0. Let's see, what did I have? 21. Multiples of 3, just like the data were given. And then 0 for the minimum, 120 for the max. And I did it in multiples of 12, that way I could have 10 tick marks. So then second, calc, choice 5. Notice the data are already plotted for us. Okay? Now the graph doesn't look exactly exponential, it looks almost straight, but it is exponential decay. You can tell it is slightly curved. Okay, at least the graphs cross. Okay, y1 is correct, y2 is correct, guess 10.5, okay. So we get 16.341998, etc. So to the nearest tenth, half-life is about 16.3 hours. Okay, remember for question D, we just want to plot the data and the graph. We just have to go in there and delete the y2 graph because we want to see that line. So for part D, let's go in here and turn y2 off. So y equal, just go ahead and clear it out. And then graph again. There. And that does look like what my calculator drew, right? Okay, now choosing the right model. Now we've looked at linear, we've looked at linear and exponential models. Now how do we know which is the best model to use? Okay, there are a couple ways to answer that question. Okay, but first be aware that any model can be used to model any data, whether or not it's the best one or not. Okay, so you can use a linear model to model exponential data. It's just that it's not the best choice, but you can use it. And vice versa. So part A, the graphical tests. In order to apply a graphical test to determine the best model, we plot the data values to see what type of shape appears. The graph of the plotted data, again, is called the scatter plot. So basically, for a graphical test, do the scatter plot, which means you have to turn on one of your statistical plots. I've always turned on plot 1. So if the scatter plot appears to make a straight line, then a linear model is the best for the data. Now, it doesn't have to all line up, but if it seems like a straight line, that they're all clustered around it, then use a linear model. That would be the best model. If the scatter plot appears to make one of the exponential graphs, it's like it's going up like that, increasing, or going down like this, decreasing, then use the exponential model. Okay, so it's kind of like you look at it and see what appears to be the best. So again, be aware that you can use any model for any type of data. Just that it may not be the best, but you are allowed to use it. And if it's not the best, you may get some really weird results. Analytical tests. These are where you actually perform some analysis. In other words, do some calculations. So in order to apply analytical or algebraic tests to determine the best model, we must first have the differences in consecutive independent variable values all be the same. Remember, that means that they're uniform. So the x values, the independent variable values, they must be uniform. If they're not uniform, you have to do the scatter plot. Okay, then we look at differences in consecutive dependent variable values or ratios. Okay, so you're going to do the differences and the ratios. Now, first of all, if the first differences are all equal or approximately equal, then a linear model is best. Remember, having the first differences all be equal or approximately equal, that means that the second differences will either all be 0 or all close to 0. So if that happens, you're going to be using a linear model as your best model. Number 2, if all the ratios of consecutive dependent variable values are equal or approximately equal, then an exponential model is best for the data. Now, if you can't remember, well, what am I supposed to do to figure out what the b is going to be, what the base of the exponential is going to be in the case of exact, just go ahead and use an exponential regression. It'll find it for you. But remember, if we call the ratio r, and it's exactly linear, then the base of the exponential is r raised to the 1 over delta x power. Remember, well, delta x is the difference between consecutive x values. That was way back in section 4.3. Some examples. Determine if each of the following is best modeled by a linear model, an exponential model, or neither one. So this is basically multiple choice. So linear, exponential, or neither. Here's our first one. Okay, the function is given by this table. X's are 0, 2, 4, 6, 8, and my y values are 14, 20, 25, 30, and 35. Okay, our solution. Okay, we're going to calculate the first differences, because do notice the x's are uniform. They're all 2 units apart. So I reproduce the table. So remember, the difference is right minus left. So 20 minus 14, 6. 25 minus 20, 5. 30 minus 25, 5. 35 minus 30, 5. Come on, make a 5. So notice, except for the very first one, they're all equal. So the first differences are all approximately equal. A linear model is best. Now, if it turned out they had not all been approximately equal, I would then look at ratios, 20 over 14, 25 over 20, and see how they looked. Because remember, if they're not all about the same, we've ruled out linear, so then you have to check out the exponential. And if you rule out, then it's neither. So graphically, we have the following. My window setting for these. Okay, so if you actually were to do the graph, so whoops, let me get out Mr. Calculator. No, I'll just go ahead and, let's see. So I guess we got to turn it back on. Y equal, clear that out. Window, what did I say I was using? 0, 10, 2, 0, 10, 2, 0, 40, 5, quit. Let me clear out my lists. 4, enter. Okay, now stat, enter. Now notice we've already answered the question. This is just, if you decided to do it linearly, what it would look like. So what do they want? 0, 2, 4, 6, 8. So 0, 2, 4, 6, 8. Oops, enter. And then scroll over to the y's, and the y's went 14, 20, 25, 30, 35. And notice all these differences were really about 5, and those differences are 2, so the slope should be 5/2, it should be 2.5. So if we just graph these, now there won't be a line because we didn't do, there won't be an actual curve drawn, but you can see they all do kind of line up. Okay. So again, they do kind of form the same straight line. So the graphical test also works on it. Okay, example 2. Here's my function, 0, 3, 4, 6, 10. Notice, these are not all the same distance apart. That's 3, that's 1, that's 2, that's 4. I can't do an analytical test. Okay. So our solution, the x values are not all the same distance apart. We've got to do the graphical test. So, second memory, let's clear out our list. Let's go ahead and do that and get it over with. Okay, stat, enter. Okay, go back to the L1. There, 0, 3, 4, 6, 10. And then for Y2, 12, 40, 10, 57, 21. Okay, let's go ahead and get a window. For my x's, it looks like I can go from 0 to 10. I'm going to go a little bit past 10 just to be safe. And my smallest y value is 12, so I'll still go down to 0. But my biggest one appears to be 57, so I'll go up to 60. So for my window, minimum of, well, let me go a little below that. Let me go ahead and say negative 5, what the heck. And for my maximum x, let me go past 10, let me go to 15. And let's do multiples of 5. And for my y min, okay, 0. And past 57, I said I was going to go to 60. Okay, that's good enough. And the scale, I don't know, 5 is good. So let's graph and see what happens. Wow, they're just all over the place. Okay, they're just really scattered. They're just all over the place. So it's definitely not a line, and it doesn't appear to be making it a shape for an exponential. So it's neither. Now what table? Let's see. I did that one. I kept it at 1. So yeah, they're just all over the place. So neither model is appropriate. Though remember, you could still use either model you wanted. It's just that it would not be very good at all. That's the end. of section 4.4.